So my name's Dan Smith. I work on the Valhalla project. And I think I counted in Brian's talk at least 8 different follow-up talks that we could give. So this is one of them, and this is the one we picked that we thought would be something interesting and new that we haven't covered before. Part of the work in the last year is we've discovered this interesting problem with initialization and realized that if we can solve this problem, that unlocks a lot of good things. So today I'm just going to zoom in on variable initialization and how that interacts with Valhalla features, and try to get really concrete with some code and talk about the language rules and the VM rules and explore this problem in more depth. Start with some motivation. Here's a dictionary definition of initialization that I thought was a good frame to think about this problem in. So it says to initialize is to set something such as a computer program counter to a starting position, value, or configuration. So there's a thing. It has the ability to be set, and we want to set it to some starting configuration. That's how we initialize it. Let's think about in Java, what sort of things do we initialize? I've highlighted the initialization elements in the code there, everything in yellow. So some examples: local variables get initialized. There's the I down towards the bottom there that as we iterate over the loop, we initialize it with 0. Fields and arrays that need to get set to some initial thing. Classes get initialized, so we're up-leveling a little bit. A class has a static initialization. It has a CLInit method in the VM. And in order to set the class to its starting position, we run that code. Same thing with class instances. When you allocate an instance, you have constructors that set the instance to its initial configuration. Sometimes an object used for a specific purpose, the class doesn't know how you're going to use it, but the use site does. And so the hash map in the middle there, part of initializing that hash map is to put a key and a value in that hash map, because in this place, to initialize it means to fill it in with the right things. And then we can up-level even more. Components, modules, frameworks, they can all be set to their initial state, and usually that involves initializing some classes, initializing some fields, so it kind of stacks on top of each other. Other thing I want to point out about this definition is it says we're going to have this thing and set it to its starting position. So what does that mean? How would you describe the position of the entity before it has been set to its starting position? It's a bit of a paradox. It has something, it is set to something, but it hasn't been set to its starting place yet. So there's something before that, and that is the source of the problems I want to focus on. So there's usually a space between creation and initialization. Often, not always, but often, it's possible to interact with the entity in that space. So call that the larval state of this thing that we want to initialize. It's not yet an adult, it's not yet fully formed, but it exists. The thing about larval entities is they don't satisfy their invariants. That's the point of initialization, to set up the state to satisfy invariants. So you've got something that doesn't satisfy its invariants, it's floating around in your program, and when you interact with it, all bets are off. You don't have the guarantees that you would have if the invariants were reliable. There's different kinds of invariants. Some of these are things developers define. So ultimately, it's up to the programmer to have their concept of what it means for this object to be created. And it's up to them to decide what code needs to go in the constructor so that this object can reach its starting state. But there are things that are kind of more fundamental that developers are going to rely on that the language and the VM care about. Things like type safety, knowing that when I look at a variable, the thing stored there is an instance of the type that I said I wanted to store in that variable. That's something that the whole system relies on. So there's this kind of domain agnostic idea of being initialized. That's the area that I'm going to focus on in our talk. Two important invariants for variables in particular that we care about in Valhalla. The first is that when you read a final variable, you're always going to get the same thing. That's what final is supposed to mean. It stores something, and when you read it, you're going to see the same thing. Second, that reading a variable with a null restricted type, Brian talked about these null restriction features. When you read from that variable, you expect to not get null. That's the point of the type. So now think about fields as an example. Is it ever the case that a field might not get initialized and might not satisfy these invariants when someone is trying to read it? In this example, class C, notice that in order to initialize the field S, I'm calling a method. So do you see the bug there, or the risk of a bug? Depends what method does. Maybe method is an instance method in the superclass. And so that superclass then has access to the object and can invoke methods, can cast it to C, can try to get to S. And if it does that, it's going to see the larval variable that hasn't been initialized yet. Similar with array components. If I create an array, say new string with 100 components, and then iterate through and initialize the components, every time I call some method and go off somewhere else, I don't know what that method's going to do. And if there's any path through the code to get back to this array, then those array components are at risk of someone interacting with them in their larval state. This is nothing new in Java. We've had it for a long time, and people kind of make their peace with it, and there are coding conventions that avoid these sorts of risks. With Valhalla, we're interested in some optimizations that these larval variables get in the way of. So I want to illustrate some of those with final fields. If I have a final field, I assume that every time I read from the field, I'm going to get the same result. On the left, there's the final field X in an object, and then the green part is a method M. And in that method's local variables, W has a pointer to the widget. Okay, it would be totally fine for the VM to decide to get to that X field and cache the result so that later when it needs to go to w.x again, it's already got it sitting there. Doesn't need to follow the pointer. If we could assume that final variables are always final, but it turns out if it's a larval variable, it hasn't been initialized yet, then you're going to see maybe it starts out at 0 and then it becomes 3. Or actually it's possible with the VM rules to set it to 3 and then later set it to 4 during the construction process. And so in its larval state, that thing can change, and this optimization doesn't work. Optimization on the right, these are value objects. So what I know about value objects is that they don't have identity. It's fine to extract their fields and do whatever I want with them and later reconstruct them if I need to. And we can freely manipulate them in that way. I've got a line object with 2 pointers to 2 different value objects. It would be convenient for density to be able to collapse those down to just 2 sets of XYZs and put them all inside of the line class. So that's what this optimization does. Again, if the P1 and P2 can change, then this optimization doesn't work anymore. Now you've got 3 different fields that have to be updated in order to perform the assignment. And like Brian talked about, you do that and you can get inconsistent states where one of them has been written and the other two haven't been written yet. This also has the same problem as on the left, where these fields, if the fields of the point class are changing, then all this caching is caching stale information. So important to have the property that final fields always give you the same result. What about null restrictions? In this case, I've got an array of month days. Month day is a class in Java time. It holds essentially one byte for the month and 1 byte for the day. Those range from 1 to 12 and 1 to 31. So just small values. They're not 0 ever. So a month day of 0, 0 would be an invalid object. In this case, the original program, in the user model, they've got pointers to different month days in this array. And the optimization we'd like to do is collapse that all down into the array. Because these are just byte values, it's actually 3 bytes. We can collapse the reference down into one true false that tells us whether this is a null or not. And then 1 byte for the month, 1 byte for the day. Because these are value objects, those 3 bytes express the same thing as a heap allocated object. And we can freely convert between the two. So that optimization is fine, the one on the left. The optimization moving to the right is to get rid of those null flags, because I've said this is a null restricted array. That's an important optimization, because now instead of 3 bytes per component, we have 2 bytes per component. Because of layout, we actually probably need 4 bytes per component because of alignment concerns. And so by moving from the left to the right, we shrink the array in half, the footprint of the array. So another optimization we'd really like to be able to do, but again, it's invalid if there can be nulls in the array, because stripping away the null flag leaves you with some zeros. And as I said, the 0th month of the 0th day is not a valid instance of this class. So to restate this broadly, the problem we're running into is there's these optimizations we want to be able to do, but these invariants that have to do with initialized or larval, not yet initialized variables are getting in the way. We can't assume the invariants with them floating around. So what's the solution? Brian gave an overview of this, a new concept of strictly initialized variables that are guaranteed never to be read in their larval state. So I called the talk Variable Initialization 2.0, where we're talking about a new model for how you initialize variables that we want to encourage, that Java is going to encourage developers to adopt, and that under the hood, the bytecode is going to adopt so that we can have the nice properties we want. All right, part 2 out of 3. Let's talk about the solution in more detail. How can we ensure that larval variables are never read? That's the goal. If nobody ever reads them, they'll never see the state before it has reached its starting configuration. I've ordered them by order of difficulty. So we'll start with local variables, static fields, array components, and then instance fields. Strictly initialized local variables are super easy because that's already what they are. The language requires an assignment to a local variable before you can ever use it. And then in the VM, the verifier requires that a local variable slot has been assigned something before you can read from it. So easy, we're done there. That includes parameters, that includes caught exceptions, all of that stuff. It works out for free. What's left is the things that aren't in a local context. things that can be shared across threads, and that's where we need to do more work. Static fields. What does this look like when you have a static field that gets interacted with in its larval state? On the right, class C has a variable S that gets assigned from a method call. You go to that method call and you see in green an attempt to read from the variable. When you do this, you've got a cycle in your initialization logic, and what you get from that read is a null. That's not really great. In this case, you would end up getting a false result instead of a true result. Nobody tells you that you read your static field before it was initialized, and the code just carries on, and there's probably a bug here. So we can change those semantics to dynamically check for strict initialization of the static field. In order to do that, we need an opt-in. So at the VM level, we decided to use the ACC strict flag for this purpose. It's no longer used for floating point strictness on methods, but it's already there, and so we thought, hey, we'll just use this. It also conveys what we want for fields. The concept, this is something that has a new strict set of rules for how it can be initialized. And so the rules are, if you do a put static on an ACC static field, if it's final, it's going to check to see if that thing has already been initialized. And if it has, it'll throw. If it hasn't, or if it's not final, we'll record that now this thing is initialized. So there's a side state that keeps track of whether a static is initialized or not. And then on the reading side for get static, we'll check that it's initialized, and if it's not, we can throw. Now it's fail fast instead of silently ignoring the error. These extra steps can get optimized away. So once you read for the first time and you've resolved the reference from a particular get static, the state of that get static instruction can keep track of the fact that it knows it's initialized, and from then on, it doesn't need to keep checking. There's also ways to optimize the metadata about whether the field itself is initialized. So in general, this sort of becomes, it sort of disappears, but you get the extra integrity guarantee. Again, this needs an opt-in from the VM. It also needs an opt-in at the language level, which we'll get to, maybe what this might look like in the language. Okay, third thing, array components. How can we guarantee that an array component is always initialized before it gets read? Really, once an array is allocated and it's an object floating around through program code, there's not much we can do without a lot of very complex analysis that's going to be heuristic-based and imperfect. So what we're after is something stronger, and we can get that stronger guarantee by asking the array to be initialized at the point where it is created. So there are existing arrays in the system that are not strictly initialized. The idea here is that somebody who creates an array could create it in a way that strictly initializes it, and that's a property of the array that can be tracked and that can enable optimizations. Today we have so A1 there, that's not a strict initialization. We don't know what's going to happen with A1 after that, and we won't try to prove that it's initialized before any reads happen. A2, it could be. As it's compiled today, it just looks like A1. There's a loop and X, Y, Z get plugged into array components, but we could compile it differently, and if we did, it could be treated as strict. A3 and A4, these are strawman syntax that provides some more convenient ways to initialize all the components of your array without needing to enumerate them. So with a single expression to fill in all the components, or with a lambda. Here's what that looks like in a library that provides this mechanism. So we already have those first two new instance with a component type and a length, new instance with a component type and multiple lengths for multi-dimensional arrays. We could have a new instance that takes in something to fill in the array, and we could have a new instance that takes in an in function that computes something to fill into each component of the array. So those are pretty straightforward, and what you get is at the point where these methods return, it's guaranteed to be initialized. As I said on this slide, we don't anticipate any sort of bytecode to do this. This is really just an API, but it can be used by the language to compile down to API calls. All right, and then finally, what do we do with instance fields? Brian talked about this to some extent. This is where there's an interaction with flexible constructor bodies, which provide an opportunity to do something in Java code early before the supercall happens. Why is that important? Because once this escapes to any external code, again, I don't know what anybody's going to do with it. I can't guarantee they're not going to try to read from a field. So we need instance fields that are initialized before the first point of escape, and the first point of escape turns out to be the supercall. Again, we can use the strict flag to mark certain fields. So some fields are not strict, some instance fields are, and the ones that are marked strict, we can then validate that they've been initialized before they get read. Specifically, that involves checking that there is a put field to that field before the supercall. That's some new verification logic. And then, if it's final, making sure there's no put fields after the supercall, so that we can guarantee that it is truly final and it's not going to change afterwards. Flexible constructor bodies divides up the logic of construction into two phases. There's the early phase and the late phase. And so in this code that I had on the last slide, I've highlighted the red parts. That's the early logic, and the blue parts are the late logic. The early logic comes before super, or even the arguments to the supercall. Also, any strict field that has an initializer, that initializer, of course, needs to run before the supercall because it's required to be DA at that point. What is unique about the early construction phase is that you can't do anything with this other than assign to some variables. So you can't directly refer to this in that code, in the pink code. You can't invoke instance methods. What you can do is assign to the instance fields. And then in the late phase, you can do all the things you're used to doing in a constructor. You can read the instance fields. You can use this. You can invoke instance methods. But what you can't do is initialize your strict fields. They need to have been initialized early. Ideally, just in general, we think it's a good thing to initialize all of your fields as early as possible. So if you can, that logic belongs in the early phase. Why do that? Because then people can rely on those fields being initialized. Another way to say this is we're thinking about an initialization model for constructors. It's different. People usually think about construction following the diagram on the left. First, the object class gets initialized, and then A, B, C, following down the hierarchy. Each class has its turn to do its initialization. The reality of the bytecode and the reality with a space for some early initialization code is that there's the early initialization and the late initialization logic. The early logic goes up the chain. When you reach object, that's the point where you transition from a larval object to an adult object. And then going down the chain, you're working with an adult object. You might be wondering if it makes sense, if it's possible to write code this way. We did some analysis of final fields to get a sense of what this looks like in real life. We looked at 2.3 million open source classes and kept track of all the final instance fields. 63% of the time, the initializer of a final instance field is provably, using some pretty conservative analysis, provably independent of any interaction with any other code. It doesn't depend on this. It doesn't have any method calls that could interact with some other method call. So 2/3 of fields, it just would work to move the logic to the early phase, nothing would change. There's another 12% where maybe those could also be moved. They don't depend on this, but they do execute some code. So think like there's a superclass that calls a constructor, and then there's a subclass that calls a constructor. Those two constructor calls might interact in a bad way, and so that goes in the 12% bucket. The remaining 25% is something that comes after a reference to this. And so if you were going to move those initializations into the early phase, you'd need to do some sort of refactoring and make sure that's safe. But even in that case, we think many of those are probably safe. There are cases where it's simply not possible because you're creating a loop or something like that, and you really need to be able to talk about this in the process of setting up your field. But those are probably pretty rare. And so we think, yeah, this is something that a lot of code can pretty easily do without disrupting any of the logic. So again, by having strictly initialized variables, I've covered all the different cases of variables. We can guarantee that nobody ever interacts with a larval variable. And if that's the case, then we get the invariants that we were hoping for. Okay, third part of the talk, I want to shift gears and talk about how does this look in applications, in the things we're looking at in Valhalla and maybe beyond in other use cases. So case studies, I want to spend some time on value object construction, null restricted types, serialization, and mention a deep reflection as well. Value object construction, a year ago, when we were talking about this, Brian mentioned that we had special bytecodes that do the initialization of the value object. And by doing that, we can get the invariant that we want. Final fields are never going to change. So we didn't use init methods. We didn't use mutation. Instead, the idea was to get an instance of the class and then have a copy with modifications operator that's with field. Create it. That creates a new instance of the class and it sets a particular field value. So you do some with fields and you've created a chain of 5 objects, and when you get to the end, you've got the fully initialized value object that you want. Notice I've got a different constructor name. This is called vNew because this is not a regular init method. This is something different. It's more like a factory. And that means that identity classes have their mechanism. Value classes have a different one. They don't interact. They behave differently. One limitation of the value one is we didn't have any support for super constructor logic. All the logic needed to be located in one static vNew method. We didn't have any support for superclass fields. Over the last year, we've thought through this. We've realized that's something we can simplify, as Brian said. And by tackling the initialization problem, it turns out we can use init methods to construct value objects. So instance fields of value classes must be strictly initialized. That's the limitation that we impose in order to get the behaviors we want. In a value class, when it's compiled, every field is going to get that ACC strict modifier. Value objects can be instantiated via mutation, but they can never be observed in their larval state. So despite not having identity, there is a larval object that has fields poked into it. And until you reach your adult state, the normal things you can do with value objects, like shredding them down to their fields and copying them over to something else, those sorts of optimizations are not allowed. In that larval state, it's sort of like a builder where you can poke things into the fields. You can't attempt to read it, you can't pass it to somebody else. But by setting up your larval value object, you can get all the fields set to their initial state, ensure they're never going to change again, and then transition through your invoke specials super.init call. When we do it this way, superclasses of value classes can have fields, they can have construction logic. Because again, go back 4 slides. All of the pink stuff is where the initialization happens. And in that space, nobody's referring to this. Nobody's doing anything with the value object. So each class can, in turn, set up its state. And then when we transition, that's when we have a value object where the invariants can be assumed and all the regular optimizations can apply. Yeah, I did that one. Okay. In the language, one thing about early initialization is it's kind of inconvenient to have to say super in the very common case that you have a constructor that just does some things for this class and doesn't care about the superclass. So in a value class, we can change where the implicit supercall happens. That's what I've illustrated here. Field initializers still go at the start, and then you have the body of your method. But if you get an implicit super, in a value class, that call can go at the end. And that means automatically all the logic in your constructor happens in the early construction phase. Which means you can't refer to this commonly in your initialization logic of your value class. Now, if you want, you can have an explicit super. And then after the explicit super, you can do whatever you want with this. You just can't initialize variables, initialize your instance fields at that point. All right, second thing was null restricted types. The default value, as Brian said, of a reference type field is always going to be null. If the variable says it can't store null, what is it going to store instead? And so the answer is you don't really have a default value, which means that your null restricted fields in your arrays need to be strictly initialized. So that brings in all the rules we talked about earlier. A variable like S1 here that has type string bang, that's going to be subject to the strict initialization rules. So in this case, I've got a static field. The assignment, when I call util.getString, that's going to be applying the rules I talked about where there's a dynamic check on that static field. That instance field S2 needs to be initialized before the constructor call. And an array of string bang needs to be constructed using one of the mechanisms that provides initial values. As a convenience, it may actually be possible for certain classes to define their own defaults and behave more like primitives in that respect. Say, here's my 0, use that to initialize arrays. And then if that were provided by the class, we could relax these requirements and we could let the compiler insert the default values implicitly. So that's something that we're thinking about. But the general rule for Bang types is they need to follow the strict initialization protocol. Serialization. Okay, so let me walk through the details of deserialization when there's something in a stream and I want to construct an instance of that thing. This is traditionally how this algorithm behaves. First, we're going to create a blank instance of the class. On my right, this is the class non-empty list. I'll create a blank instance of that. All its fields will be null. Step 2, I'll invoke an init method as usual, but instead of the regular init method, I'm going to invoke the init method of a superclass. Often that's just object.init. So the serializable class doesn't get its init code executed. It's some superclass. And that transitions it to sort of an adult state, even though some of the fields aren't initialized yet. Step 3, we store that object in the deserialized object map, and that's used for later on whenever anybody needs to look up a particular object in the stream. There's a map that gives them the object corresponding to a certain key. So we store it in the map. Step 4, deserialize all the field values. And step 5, write those field values to the fields of the class. So at step 5, that's where we can say we've initialized all the fields of the class. Do you see the problem with that? It's step 3. Step 3 is where we publish the object in its larval state. And anybody who interacts with that map, including any of the deserialization logic for my field values, I think also any of the deserialization logic in a subclass or in a superclass, either way, all of that is going to be able to see the larval object. So strictly initialized fields aren't compatible with this mechanism. Instead, we need something different. This is sort of an early design stage. We've talked about how can we make serialization better. There are many reasons for this. The initialization problem is just one of them. But here's an updated algorithm that works correctly and safely. First, store null in this deserialized object map. So the key that people are looking for, it's just going to get null out of the map. Second, deserialize all the field values without having published this yet. Step 3, allocate a blank instance. Step 4, invoke a designated constructor. In this case, we're just going to use a regular constructor of the class. We're not going to do any magic where we're invoking some superclass constructor. No, it's just a constructor of the class non-empty list. And then step 5, store that object in the map once it's fully initialized. So the publication doesn't happen until initialization completes. One thing to note about this is exactly how records get deserialized. We added records a few versions ago. Rather than modifying the records as you go using the usual process, we said, hey, there's a constructor that knows how to create instances of this record. So let's just use that thing. And similar to what we're doing here. The difference is I need to mark that constructor somehow. So I've marked it with a made-up keyword here to say this is the way that you create instances from a stream or from externalized format. Just a couple words about deep reflection. This is a similar problem to deserialization. So today we have a set accessible method in field lets callers turn off instance field finality. That seems really weird. That you can go into reflection and you can say that final field, actually it's not final anymore. And once you turn it off, you can go in and assign whatever you want to it. It can be mutated freely. What is the use case for this? It really comes down to somebody outside of the platform, some third party that wants to create an instance and then fill in the values, much like deserialization does. So typically they need a no-art constructor that's just gonna start this object out with some nulls and then fill them in later. And so they wanna turn off finality because they wanna pretend they're living in a constructor, basically. Again, that's not something that's compatible with the invariants that strict initialization promises. In the example code, notice that the first constructor, where I assign a null, that's breaking the requirement of the field's type because that field is null restricted. So how can we do this better? What we really want to do is encourage people doing this process to do the same thing deserialization does, go to a constructor that's been designated for this purpose. This is how you create instances of this class. And pass in your parameters directly. Leave it to the constructor to do the logic. Because again, the VM and the platform can guarantee that the logic inside the constructor is interacting appropriately with strict instance fields. To conclude, some points. We talked about how larval fields and larval arrays violate the invariants that we need to rely on. For some features, we really need those invariants to be reliable, not just mostly true. So for some fields and arrays, we need a new initialization model that gives us guarantees, avoiding any risk of interaction with the larval state before it has been fully initialized. Strict initialization asks programmers to change their code. It asks them to write using certain patterns that might be different, that are a little more disciplined than the more relaxed code format that they're used to. In return, they get better safety. And we think that's a worthwhile trade on its own to solve some of these safety problems that have been there for a long time in the language. It also unlocks performance improvements that you can't get without being willing to follow that discipline. This one thing unlocks a lot of things. We can get compatible value class migration. We can get reliable runtime null restrictions. We can get safe flattening of large value objects. All these things come along for the ride once we've worked out this initialization problem. And like Brian said, this wasn't an obvious solution to the problem. We were looking at those problems as in their own terms. And it was interesting that this thing is sort of at the center of all of them. Fix this, and those other things fall out. So that's a nice outcome of this design effort. Last slide, just want to mention that this isn't one monolithic feature that's going to be coming out in a particular JEP. Value classes and objects rely on it in some ways to ensure that the final fields are never changed after the supercall. Null restricted and nullable types need some additional logic. They need the ability to prove fields have been assigned and so they're not null before the supercall. They also need the array creation capabilities in order to create arrays of null restricted types. There's, like I said, work in progress for a new serialization. A lot of good ideas there that are working their way towards a fully fledged feature that we'll put in a JEP. And the key here for our purposes is the designation of a certain constructor as the way to construct instances. I haven't mentioned, what about this feature more generally? Can I use a strict modifier? Well, probably not. That would be bad in a few different ways. But are there other ways that we can let people opt into this behavior in the language? We're thinking about that, thinking about other kinds of classes and other implicit ways that we can give people a chance to opt into this. So that's all I have. I'm also over time, so maybe I'll stop here. But that's it. Thanks.